Hi, welcome to lecture 6.3, Density and Mass. So today we're going to be talking about an application of integrals to some physics ideas and physics questions. So you may have heard of density and mass, and we'll talk through some examples. And we'll see how we can use an integral to answer a question like, what's the total mass of this object when it has a density that's varying? So different density at different points in the object. So let's just remember what mass and density mean from physics. So mass is just like the amount of matter, amount of stuff that something contains, and it's just measured in units that use grams if you're using metric, kilograms, and it's just a measure of sort of how much stuff there is. So, for example, a big rock, boulder, could have a mass of 1,000 kilograms. So bigger thing has more mass. It's important to distinguish the mass from the weight. So weight is a word that means how much gravity is affecting you, the force of gravity on you based upon your mass. So you might have heard of Newton's law, force is mass times acceleration. So if something is feeling the pull of gravity, so if I have my 1,000 kilogram boulder, right, the kilograms is just a measure of like how much stuff there is, and if it was in space, it would still be 1,000 kilograms, and if it's on Mars, it would still be 1,000 kilograms. But the weight that it feels depends on where it is. In space, it feels no weight. On Earth, it feels some weight. On Mars, it feels some other weight, and that weight depends on the force of gravity. So on Earth, gravity is measured as the force, the acceleration due to gravity is this number. It's something you could measure if you do like some experiments, and it's this number, negative 9.8 meters per second squared. So the idea is the rock, when it's just sitting on the ground, it feels this force of gravity, and that would be a stronger force if we were on a different planet or whatever. We can just compute the force due to gravity that it feels. It's the mass, which is my 1,000 kilograms, times the acceleration, this gravity number. I'm writing the parentheses just so the minus sign is clear. And so we just multiply these two numbers. So you get negative 9,800. You kind of combine the units like this, so kilogram meters per second squared. We'll come back to that in a second. So all this number really means is that the amount of force that you feel, that the rock feels, depends directly on both its mass and its acceleration. Directly meaning we just multiply the two numbers. So this is like something people observed experimentally when they were kind of coming up with physics, that like if I make the rock 2,000 kilograms instead, then the force is twice as strong. Right, that's not super obvious. Like maybe you could imagine if I double the mass of the rock, maybe that quadruples the force or something like that. But it turns out from experiments, the most accurate law that people came up with was that it's just mass times acceleration. Double the mass, doubles the weight, doubles the force. Or if you doubled the acceleration, went to some bigger planet that had twice this g number, then that would also double the force. So that's maybe the interesting thing about the law, is that it's just directly proportional. Double the mass is double the force, instead of some other rule, right? So anyway, this kind of English word weight, when people are talking about physics, they mean specifically this force due to gravity. So the weight of the rock is the force due to gravity. Okay. Yeah, and then one thing maybe about the units here, because we just multiply these two numbers, it kind of makes sense to sort of multiply the units. And this chunk of units, kilogram meters per second squared, is so common it gives a special name. They call it a Newton. So N for newtons. Just sort of named in honor of Newton, I suppose. Okay. Something else just to mention while we're here is that there's a difference in the vocabulary here between metric and standard units. So the pounds that we use, is technically a measure of weight, not mass. So it's not that big of a deal, but the way it's set up, like this G, this 9.8 thing, is sort of already multiplied in when you measure something's weight in pounds. Because when you measure something in pounds, you're measuring it like on a scale, and the scale is sort of like already being affected by gravity. So like, if I measure something's pounds on Earth and it's pounds on Mars, I'll get different numbers. I need to do some division or something to figure out what their true mass is, which would be the same between the two planets. And confusingly, if you have a metric like bathroom scale, it will just measure the weight and report it as kilograms. So that's also kind of like it's doing a division inside in electronics to give you the mass, I suppose. I don't know exactly how that works, but the point is, if the problem says like what's the weight, they might tell you the G, and you might know that you're supposed to multiply the G. Again, this isn't physics class, so I'm not super worried about it, but I'm just trying to give some context so you feel like you know what's going on. Okay, so yeah, that's weight. There's also density. So density is just a word that means how much mass do you have per volume, or per length, or per area. So, right, if my boulder that's 1,000 kilograms, if it's a really small boulder, if it's like a foot wide, that's really dense. But if it was like 20 feet wide, that'd be really light, right? And in fact, because it's a rock, you probably have an idea of how big it probably should be, and that's to do with the density, right? If I had 1,000 kilograms of feathers, that'd be huge. It'd be like a truck full or something. Or if I had 1,000 kilograms of, gold or something, it'd be a lot smaller because it's very dense. So mathematically, we just have to do a division. I'm going to take the mass and divide it by the volume. And that number, I call that number the density. So let's look at this example. So my rock, my boulder that's 1,000 kilograms, suppose it's a sphere, radius 1 meter. So I'm going to take my mass, which was 1,000 kilograms, and I want to do the volume. And I'm going to do the mass divided by the volume to get the density. How do I get the volume? Well, I have to know the volume of the shape. The problem says it's a sphere. I have to know the volume of a sphere. So you might know that the volume of a sphere is 4/3 pi r cubed, where r is the radius. Again, that's something you could look up if you didn't know. Here, the radius of the sphere is 1, so we're just going to get 4/3 pi. So that's my volume. Since the radius was given in meters, I probably want to say meters cubed, so cubic meters. So now we can get the density. So the density is the mass, which is 1,000 kilograms, divided by the volume, which is 4/3 pi meters cubed. And we just get some number, 1,000 divided by 4/3 pi, whatever that is. And like before, we kind of float the units together like this. And we kind of think of this kilograms per cubic meters as like a unit of how dense it is, right? If I have a lot of kilograms per cubic meter, that's more dense. And if I have, that's like the gold. If I have a small number of kilograms per cubic meter, that's very dense. It's like, or less dense. That's like the feathers. By the way, this number ends up being about 238. So 238 kilograms per meters cubed is the density of the rock. And this like division, this per, you should really think of it as like counting in groups, right? It's per meters cubed, per cubic meter. So that means if I take a cubic meter, like I take a meter and make a cube out of it, right? That's a really big chunk. Apparently, if I have that much of my rock, that would weigh, the mass of that would be 238 kilograms, apparently. That actually sounds really light to me, so I think I made up a bad number, right? Imagine a cubic meter, like it's huge. It's like the size of a car, and it's only 238 kilograms. That's a human is like 1 or 200 kilograms, right, or whatever. So anyway, so it's good to kind of just like think in those terms, right? If I had 3 of these cubic meter cube rocks, setup, that'd be 600 something kilograms. Okay, so that's density. So let's look at this example first. So another kind of density, this is like a volume density, but sometimes you say like a density per length or per area, just depending on how you're measuring the object. So here, thin copper wire has a constant density of this number, 0.00279 grams per millimeter. So how much copper is in the wire if it's 3 meters long. So again, right, this is grams per millimeter, right? So I want to think of that as, like, here's my millimeter, and it sitting inside that millimeter is a small number of grams, right, sitting inside my 1 millimeter. So, you know, if I had 2 millimeters, right, I would have 2 times that number total grams, right? And if I had 3 millimeters, I have 3 times. So I just have to do multiplication to figure out how many total grams I have in my 3 meter long wire. So it's just multiplication. The only thing that's a little bit tricky here is just the arithmetic, because I want to go from millimeters to meters, right? How many millimeters does it take to get all the way up to 3 meters? Well, you have to know the system, but there's 10 millimeters in a centimeter, 10 centimeters in, or 100 centimeters in a meter. So I'll have 1,000 times, right? I need to have 1,000 millimeters sitting inside 1 meter. So in 1 meter is whatever this number is times 1,000. And so in 3 meters, right, you just kind of have to think about this. In 3 meters, you get this number times 3,000, right? So whatever that turns out to be, I think I get about 6 here, and that's 6 grams. So again, it's the same concept. You know, you use multiplication, use division. Just this, in this story, it's a thin wire, so I'm just multiplying by the length. In reality, you probably, like, the thin wire is actually like a filled-in cylinder, like a tube at some level, right? Probably. And so you really want to, like, multiply by the volume. But when it's really thin, we just kind of pretend it's sort of one-dimensional. Or another way of saying that is, like, you assume it's like a constant width, so in each cross-section you could just multiply, and it's fine. And, you know, for real life, that's a perfectly fine approximation 90% of the time. Okay, so this is not calculus, right? This is all just sort of physics and multiplication and, like, basic stuff. This is only so multiplication, because I'm assuming a constant density, right? The boulder, everywhere on the boulder is the same density in my story. Everywhere on the wire is the same density on my story. But you could totally imagine objects which have different densities depending on what part of the object you're on, right? For the wire, for example, maybe the wire is thicker at the beginning, but then gets thinner and then gets thicker again, or something like that. Or for the rock, maybe it's actually a conglomerate of a couple different types of rock, right? And some of the rocks are lighter than other types of rocks. So in real life, the density is typically not a constant, unless it's just like a pure, like, you know, factory product or something, right? Usually it's not a constant, and it would still be cool to, like, figure out what the total mass is, right? Now, with the rock example, if it's like stuck together a bunch of rocks of different densities, you could theoretically, like, measure the volumes of each of those individual rocks and, like, multiply it all up, right? But that's still, like, a density that is constant on small regions, right? Like, this rock is this dense and this rock is this dense, and then you stick them together. We're interested in even weirder situations where the density is actually, like, smoothly changing, right? So the wire is a good example. Like, imagine a wire that's sort of shaped like this, that's, like, thicker at the beginning, but then is, like, smoothly thinning out, or something like that, right? That's the kind of situation that we're interested in. If the density of the wire, if the thickness of the wire is sort of changing as you go, or the density is changing as you go, you can kind of imagine the graph of this, right, as like a continuous function. And something something, it's a continuous change, so maybe I'm going to integrate instead of just adding, kind of thing, right? So that's what we're going to do. So we might say an object has a linear density function, meaning that it has a density which changes as you move along it. So like the wire, for example. So maybe here is, more dense. At this x position it's more dense, but at this x position it's less dense, for example. And maybe I know not just that it's more and less dense, but very specifically there's a function of how dense it is, right? Maybe I'm saying like, okay, maybe I have this function that I'm calling rho. This is the Greek letter rho. People use it traditionally. Maybe I have a function of x which says exactly how dense it is at different spots. Right here it's this dense, whatever that y value is. Right here it's this dense, whatever that y value is. Right here it's this dense, whatever that y value is. Right? It goes down and then up. So if I have a situation like that, I can find the total density, and it's really just the Riemann sum idea again, just applied to this like physics situation. I imagine that on a little piece of the wire, I pretend it's constantly dense right here, right? So like if I imagine sort of approximating this rho curve that I was drawing by like something like this, right? I pretend that it's flat, constant density over small chunks. Because if it is constant density over small chunks, then I can just add up these rectangles using multiplication, just like we did on the last page, and that would be a good approximation of the total mass. Right? I multiply a little bit of width here by a little bit of density here, right? Width times density, that gives me a mass. So I'm getting a mass on each of these. And I can just do that multiplication if I had a function that was constant but in chunks like this. Constant and then some different constant and some different constant. So we've done this before, right? I imagine it being constant over small chunks like this. That lets me do multiplication, but then I imagine that the chunks are getting smaller and smaller, right? And if I get smaller and smaller flat chunks, maybe that's approaching really something like the continuous, like total mass. That's the idea. It's cool, I think, to have that big picture in mind. However, to actually do the problem, it's pretty simple. You just have to know that you're supposed to integrate the rho function. So let's read this example. A thin copper wire is 3 meters long, has a density that depends on the position x along the wire. Okay, that's our situation. If the density is given by this function, rho of x equals 2x plus 3, how much copper is in the wire? Okay, so we give then a density function. We know the length, 3 meters. So we're just going to integrate 3 meters. So from the beginning, 0, up to 3 meters, I'm going to integrate the density function. That's it. That's all you have to do. Right? How did I know it was 0 to 3? It's technically sort of like not really said in the problem, but usually if you're imagining this wire, right, it's 3 long. When they give us this density function, that has to be like, that's assuming that you're like starting at 0, right? It says x is the position along the wire, so that only makes sense like from the left end of the wire going down the length of the wire. X is tracking, right? How far along the wire am I? And I better start at 0 at the beginning of the wire and go all the way to 3 at the end of the wire, right? So that's kind of reading between the lines a bit, but typically it's just going to be that. Theoretically, they could say, like, set up your coordinates like 1 to 6 or something, but there's pretty much no reason not to do the 0 to 3 thing. I guess 1 to 4, right? Okay, so yeah, we just integrate the density function. The only thing that's hard maybe is just conceptually, like, what does the density function mean? And you should just think of it like this, where it's it's more dense in some spots and less dense in other spots. And I have a function which tells me exactly how dense it is at different spots. Okay, cool. Yeah, so we can handle objects with variable density. And people actually do this, when they're like, I mean, they probably have their software do it for them these days, but if you're, machining a part or something, you might actually want to know if it's thicker and thinner some places versus other places, what the total mass is going to be, right? Yeah, and then this is, an integral you can do. I'll let you do it, but I think you end up with 27. Okay, cool. So that's linear density. So when it's just the density along the wire, you just integrate the density, easy peasy. The other example that comes up in this class is the radial density function. So this is a little trickier to say, but it's pretty much the same idea. Imagine, like, I think a good picture to have is like a cymbal, like a musical cymbal, right? It's it's a disc, right? But it has like this radial symmetry, and maybe it's thinner on some parts of the disc and thicker on some other parts of the disc, right? Like maybe from the side, maybe it looks like, I don't really know what a cymbal looks like, but maybe it looks like, something like this or whatever, right? It's thinner on some parts and thicker on other parts. So we can think of that as having a density that varies. But because it's a rotated symmetric disk, right? I imagine that it has the same density on a given circle, right? Since it's nice and symmetric, I imagine like, oh, all along this circle, whatever density is here at my cross section, it's going to be that same density all along that particular circle. If I pick another position, another radius position, maybe that's like here now. Now on that entire circle, it's the same density on that circle. So it's not the same density everywhere, but if I stick on a given circle, it's like the same density the whole time on that circle, if that makes sense. And that's because, you imagine like taking this cross section and like spinning it around, right? Spinning it around this axis, right? And, we just did shell method where we were thinking about rotating stuff around an axis. And there's a straightforward way to think of this as finding the volume using a shell method. So remember, we're not literally finding a volume. We're trying to find a mass. But the math sort of works out the same as if you were finding a volume of something whose height was given by this row function. So basically, we're going to expect to see a 2 pi RH kind of thing show up, but R is going to be like my position from the center, right? Here's my center, and I'm going to have a position which goes out, right? And at a given x position, that's all the same density along this whole radius. That's the same density. The height is going to be my row, basically. So again, you can think about what's going on, but for applying the formula, all you have to know is that they tell you it's radial, and then you have to use this integral. So I'm going to integrate from the middle out to the outside, the outer radius of my disk, and I'm going to be integrating this thing, 2 pi RH, you should think. But it's your x value, and then a row of x. That's your density at that x value. So it's similar to the linear density, but basically because you're spinning this thing around, we get this 2 pi, we get this RH thing. Okay, let's read this example. How many grams of pollutant? All right, so this is not a symbol anymore, but it's okay. We can still do this. How many grams of pollutant can be found in a 20-kilometer radius from a factory that has a density of pollution this function? This should be R here. Sorry, R. Row of R. So give you radius. I'll tell you the density. The density only depends on the radius. It doesn't depend on anything else, and it's whatever this formula says. R is the radius from the factory in kilometers. Right. So again, we have the story. What is the factory? It's spitting out pollutants, I'm checking a 20-mile radius, right? This is 20. I'm checking the 20-mile radius. I'm assuming that on every circle, it's the same density, right? That's what this formula says, that it only depends on r. The only variable you see in the function is r. So r, the radius, the distance I am from the center, tells me what my density is. I want to add up all that density. I want to integrate all that density. That will give me a total sort of mass of whatever the thing my density is measuring, and it's measuring the pollution. So the total mass of the pollution. So the only thing we really have to write down is what my outer radius here is, which I said was 20. So that's where the 20 is going to go. And then I just copy my formula. I'm going to have, I'm going to write r here instead of x. So I'll come back to that in a second. And then, so that's my times r, and then times my rho, which is 40 e to the minus 0.1 r squared. So that's my rho dr. So I like to use, I probably should have written r here. I like to use r when I do this because it emphasizes that it's the radius. My radius is moving from 0 to 20. But remember that the math doesn't care what name of the letter you use. I could totally put x's here and just make sure that this is dx, and this is the same number, like these are equal. So it's nice to use r because you're talking about the radius, but it's the same number in the end. Okay, so yeah, so again, this is just an integral. You can do it. You'll get a number, and that's, you want to think of that as the total mass. Maybe we'll just mention a little bit like why this has to do with shell method. If you imagine like this mass function, this rho, like viewed from the side, my r is going from 0 up to 20. This mass function looks like something. I don't know exactly what it looks like, but maybe something like this. So if I think of this height of the function as my density, then like the total volume of the shape I would get when I rotate this around the axis here is sort of telling me, like the volume of this shape is sort of telling me my total pollution. Right? The height is like the pollution at that spot, so the volume is something like the total pollution over the whole thing. And if I think about finding the volume of this shape, shell method will work because of how we set it up. And this formula looks pretty much like the formula for shell method. So you can think more about that if you're curious. Okay, so yeah, so we talked about density. The main upshot is you just integrate. If it's linear, you just integrate the density function. That's it. You might have to think about the bounds a little bit. And if it's radial density, again, you just integrate, but you have to do this sort of shell method version because it's radial density. You'll know it's radial density if they say so, or if they say something like the density is like in terms of the radius from the source, from the center. That's how you'd know. Okay, cool. Thanks for watching, and see you next time.